If you start the PPT, it will come.
It is not there. I could not find my mouse here.
It's an extended. Now search whatever there in your system, it will be shown. It is just the duplicate.
Okay. Okay. So now we compared the throughput performance with the number of grant-free users. Here, what is meant by benchmark is our previous work, the semi-grant-free, the previous work throughput maximization with those constraints. The previous work we considered as benchmark. So previous work we assumed that no collision. So the previous work we considered as benchmark. So here, for the when you change the number of users, grant-free users, so for light traffic, so the hybrid and competitive are similar. So here the hybrid and competitive for 8 users similar. So when you further increase, so the when you increase the grant-free user further, so the competitive, this one, so the throughput decreases compared to the hybrid one. So when you take the cooperative one, so up to 12, it is better than the benchmark, the previous results. So after that, the worst performance for cooperative users, because so when you have more users, so cooperative scheme says that all users should succeed. So if you have few users, the chance high. But if you have 12 users, you get the reward if all 12 users succeed. So that's what here the cooperative performance, when the number of users increases, it is worse. So similarly, so we compared the collisions with the number of users. So the number of grant-free users, the collided users. So when we compare with the other methods, hybrid deep reinforcement learning, so here the hybrid one, so the average collided users will be less here. Then here the number of power pool levels here and the throughput here. So when you increase the number of power level, it is obvious that collision probability will decrease, because instead of having 4 power levels, if you have 8 power levels, you can reduce the collision. So that's what here the collision decreases when you increase the transmit power levels. So again, hybrid scheme, so it uses the benefit of cooperative and competitive. So that's what it performs better than the other scheme, because it utilizes the benefits of both. So same thing, similarly, the other power levels versus collision. So when you increase the number of power levels, collision will decrease. It is obvious, because you have more choice to select. So then collision will automatically decrease. So then we considered the different packet arrival rate. So lambda is the packet arrival rate with a different arrival rate. So we compared. So lambda is equal to 1, 2, 3. So average number of active users in single slot increases with the arrival rate. So these are some other numerical results. So here with different arrival rate. So here the successfully decoded users. So if more packet arrive, so the collision will occur. So therefore, the successfully decoded users will automatically decreases because more packet arrive. Lambda is equal to 3. Okay, so these are the this is the third work about collision analysis. The last work in Grand Prix NOMA. So resource allocation based on the load and location. So here earlier in previous 3 works we haven't considered the location. So and here we are going to consider the location in resource allocation. So here we are going to have huge number of users, where different traffic pattern, different locations. So here we have the collision problem. So how to avoid the collision? So here we have the we have to overcome the latency and congestion and many other issues we have to solve. So therefore we have to allocate the resources efficiently. So here again, so what we are going to do, the first base station, find the percentage of active users. So then the number of sub-channels allocated according to the number of active users. So then here we are going to have the agent, that is Grand Prix user is the agent. It is going to determine the optimal power level and sub-channel. So here when you take the location, here this is the base station. So we are going to have different grid, so circle. So within that circle, so we are going to have different regions. We call like tier 1 from theta 1 to theta 2. So that means here we have in tier 1 we have 3 regions. One here, this is 1, this is 2, this is 3. So in every tier we have 3 regions. So here in this example, here we have 12 regions. So devices are going to be not uniformly distributed. Maybe more devices in this tier or more here. So according to the locations of the devices, we have to allocate the resources. For example, say if you take a urban area, in this area the houses are too congested. So in this region you are going to have too many smart meters here. So here the houses are very far apart, so less devices. So therefore geographically the devices may not be uniformly distributed. If the devices are not uniformly distributed geographically, then resources also we have to consider the geographical distribution to allocate. So now here we see we split the cell area into certain number of concentric circles. We had a circle. So then we divided the into, so in that earlier example we divided into 4 regions here. So that region we call the tier. So then we have G number of small regions. So here the G is 12. So here 3, here 3. So here small regions, here in this example, here we have 12 small regions. So when we have this G number of small regions, each small region is defined by these 4 parameters. This is the outside radius, this is the inside radius, this is the angle, starting angle and end angle. So that means this region, say this region, for example, this region is defined by this radius, then angle starting θ1, then this angle θ. So every small region is defined by 2 radius value and the θ1 and starting angle here. So now we are going to have the matrices for all regions here. So here the first matrix. So here the each grid in each row here. So grid 1. So here the radius and the corresponding angle. Here this matrix, the distance Dij, distance of a user located in the ith tier and jth grid. So here we divided the regions into number of tiers and number of grids. The grid is here, these circles form the grid. This is one grid, second 2, the grids are here, 1, 2, 3. Tier we use this region, tier. So say for example, if you take this region, grid 2, tier, this tier and this grid. So now the locations we can, based on the distance of a particular user in the ith tier jth grid. So now receive signal power from a particular user located in a particular grid and tier, the small region considered as the grid and tier. So here this is going to be the receive signal power at the base station, transmitted power and the channel gain. So decoding again, so here non-orthogonal multiplexes. So decoding according to the power level, highest power first, then the second according to this one. So if you take a particular user, youth user in a grid Ij, in the ith grid jth tier, tier I jth grid. So we can write this is the signal power. Yes, this is the signal power. Noise power is going to be the remaining users up to u minus 1 we decoded. So from u plus 1 to the remaining user gives the interference and the noise. So this is the procedure here. So one particular user in a small region is going to send a preamble to the base station. Once the base station receives the preamble from a particular user from a region, estimate the load in that region. Say here you have 100 users. So 100 users send the preamble. So based on that, it can estimate the distance. So then it is going to calculate the number of sub-channel for each region. Then broadcast the sub-channel based on the load. So once the devices receive the number of sub-channel, then they are going to find what is going to be the optimal power level here. So here, so the optimal number of sub-channels and power levels, so we are going to select according to the load in that particular region. So here, this is the optimization problem here. So optimum number of resources for each region to ensure the fair resource allocation, so without wasting the resource. So here we are going to sum rate maximization. So that is, so here we have small regions. So the grid and the tier, the number of users. So this is the sum rate. So here we have certain constraint. So here every user has a threshold rate. They have to achieve this rate. So each user has a maximum power limit. So then here one particular user can be it's going to be in only one region. So not in at a particular time, only in one location here. So here these are the constraints. So first one is decoding order. Second one, the sub-channel selection. So only one channel. So user select a particular sub-channel. So then the resources allocated should be less than or equal to the resource pool. So then the minimum rate requirement for each user. Then for each user, they have a maximum transmit power constraint. So these are the constraints here. So again, now we are going to see the agent. Agent is going to be the grant-free user. So their agents are going to make the decision, action. So every agent is going to select a particular channel and particular power level. So here these are the action agent is going to take. State means, so each user, so once they select a sub-channel and power, so they are going to have a data rate. So every user 1 to user u, they have a specific rate at a particular time slot t. So when we use the sum rate in each tier, so this is a particular tier. So if they achieve that the sum rate, if the constraint also satisfied, then we say we can give the reward, otherwise no reward. So that means if the constraints are not satisfied, then no reward. If the constraints are satisfied, so sum rate is going to be the reward. So they meet the constraint, so the reward is given as sum rate. If they don't meet the constraint, the reward is going to be 0. Okay, so now we are going to have exploration and exploitations. So now we see, so 50% of the time is exploration. Exploration means take the action based on the Q value. Which action give high Q value? So that is exploration. Sorry, exploitation. Exploration is randomly you select. So here, so the number of users are going to be the number of agents. So their data rate form the state space. So if you have less number of agents, less number of states. So here if you take, so what we have done, so for each region, so here we have 4 regions. So region 1 to region 4. So then we compare the grant-free, conventional grant-free NUMA. So here, so and here we have the proposed this sub-channel selection and power selection scheme, and we found that, so here if the load distribution is like this. Say here we have, so the most of the devices in tier 4. So tier 1, it has only 4 devices. So similarly, here also 4 devices. So when we divide into 4 tiers, so here each region have different number of users. So when you have little number of users, we are going to have the number of states less. So if you take region 4, it takes long time because here, so it has to explore the environment because the number of states will be high because here we have more region. So if you see the region 1, only 4 agents. So since it has only 4 agents, so within 60 episode it will converge. So if you take the region 2, so and region 4, if you take region 4 is large number of users here. So when you have large number of active users, so say this is the load based one, this is the conventional exploration without considering the load. So if you take the after certain training episode, so the one we consider the load, so the reward is slightly higher than this one without considering the load. So another advantage here, say here. So here, if you take this example, so we have 4 tiers, number of users 25 users. So then, so here we allocate the sub channel. So based on the number of users here. So if you take the action space, say we have to select the number of channels and number of power levels. So here we have, when you have more users, so here we will end up with more action space. So when you take the state space, so when you have 4 users, 4 into 1 multiplied by 9, this number of states you are going to have. When you have 3 sub channels, so here we have this number of state space. But if you don't consider these different tiers, then if you have conventional all 25 users, so here total space, if you add together 63, total sub channel here 7, so huge number of state space we are going to have. So by dividing into regions, we can reduce the state space, we can reduce it. Say here, what is meant by state space here? So here state, so within that particular region, so here the how many users rates are going to be the state space. So then the action is going to be the sub channel selection and the power selection here. So now if you take so when you divide the cell area into different tiers, so it will reduce the state space of the for each agent, because we have to consider only the one region we have to consider. So in this region we have only 4 users we consider. So if you don't consider the region, we will have to consider all 25 users together. When we consider all 25 users, so here every agent only within that tier. So here if you take all 25 together, so they are going to, all users are going to select all possible 7 sub-channels. So here, if you take this tier 1, it can explore only one sub-channel. It cannot go to the other sub-channels because here only one channel is allocated because here has 4 users. Here 4 users, 1 channel. 7 user, 2 channel. So here 3 channel because more than 8. So, but if you don't divide into tier, all 25 users will select these 7 channels. So the number of states is going to increase exponentially. So by this way, by dividing into different tiers and allocating the channel, we can reduce the number of state space, this plus this plus this plus this. So this total number of states will be less than if you don't divide into tier. So by that way, we can reduce the state space and we can they converge easily. So if you don't divide it, so here 25 to the power all possibilities you are going to have. So here action space depends on the power level. Say here, for example, if you have 9 power levels, 1 channel, 1 into 9, 2 into 9. Here, the number of power levels in each sub channel. Here maybe 12 because when you have say here this action space depends on the number of power levels. This one maybe why this one is this one should be 27, maybe typo, I don't know. Because the action space only 1 channel, or then the number of power levels only you are going to select. Here 2 channels and 2 into 9 power levels, so 18 possibilities are going to have. Here 3 channels, this one should be 27. Why there may be typo, I don't know. This is 27, no? Yeah. Yeah. So here 3 into 9, 27. This is typo. So 9 power levels. So that's what 1 channel, 1 into 9, 1 into 9, 18. 3 into 9, this is 27. Here it is correct. 3 into 9, 2 into 9, 1 into 9, 1 into 9. Here 7 into 9. In 1 sub channel, 9 power levels. So this is typo. This is 27. 1 channel, 9 action. Because we fixed 9 power levels for each channel. So here allocated channel is 1. Within that 1 channel is going to select 9. So here allocated channel is 3. Within 3 you are going to have 9 power levels. So here the channel 1, channel 2, channel 3. So here power level 1 to power level 9. So all these are possibilities. All these are possible actions. So this is the advantage of dividing into regions. Yeah. So if you don't divide into regions, so here you are going to have this number of states. So the computation will be very high. So when you divide it, So you are going to sum up all these together. When you sum up these four, that is much smaller than if you don't divide it. So that is the main advantage of yeah, yeah. So that is the main advantage in this table. We can reduce the state space, because if the state space is huge, then you'll have to explore all the states. So by this way, we reduce here in the region 1 only this much, region 2, region 3. When you sum up here, 25 to the power 63, very high. So that is the motivation, that is the idea of this work. Then we have done the network throughput, then the conventional one and the equal resources. So here allocating the resources, considering the load in a particular area will definitely improve the throughput. So here for region 4, we have to have more channels. So that's what here we get throughput high. Okay, so that is the end of this one. So now, so in summary, so the previous part we considered the narrowband IoT, the narrowband IoT, the 9 parameters, and the random access control. In these 4 works, we considered 4 different scenarios. So here we have distributed agents. So in narrowband IoT, the agent is in the base station. Here agents are, all the devices are going to be the agents. So here all these devices, so when you have massive IoT, maybe 10, they can compete. When you have huge number of agents, cooperation is not possible. So the cooperative is the best, sorry, competitive is the best solution, because when you have thousands of devices, then be competitive. Finally, then when you divide the region into certain tiers and allocate the load resources accordingly, we can reduce the number of state spaces. By that way, the agents can quickly converge. No need to explore all the states. Significantly, we can reduce the states. If we divide into more regions, here divide into 4 regions. If we divide into more regions, so we can reduce the state space number significantly. So that is the motivation of this one. So in this, tomorrow, we are going to consider critical IoT. Other one is critical IoT. So next lesson, so tomorrow, about the critical IoT. Critical IoT is ultra reliable low latency communication is the critical IoT. So in 6G, we are going to have a new use case, that is massive ultra reliable low latency communication. So in the massive ultra reliable low latency communication, the requirements are massive connectivity, ultra reliability, then low latency, very low latency. All these 3 requirements, what would be the potential solution? And we have analyzed the performance, say, to reduce the latency in the 3GPP standard release 16, they proposed multiple configuration grant. So what is single configuration grant and what is multiple configuration grant, we will see later. So if you take the 5G new radio, you have numerology, the minute time slot. So if a packet, say you have time frame, this is one time frame. So if a packet arrive in the middle of a time frame, if you have single configuration grant, that device will have to wait till the beginning of next frame to transmit the data. But then that will cause the delay because you have the frame here you have. So when a packet arrives here, it will have to wait this time to transmit next time slot. So that's what in 3GPP release 16 they proposed multiple configuration grant. So that means here we have the different sub slots. So it can transmit immediately by selecting the suitable subframe. So more details I can provide in the tomorrow in the sketch diagram. So multiple configuration grant recently proposed in the 3GPP standard. To having multiple configuration grant, we can reduce the latency less than 1 millisecond. Topic tomorrow, I will bring the important slides. There are more than 150 slides in that topic. So I will bring the most important slides such that I can cover everything, the most important part of critical IoT, the machine learning in critical IoT. Okay, see you tomorrow.